Good morning and welcome to AP Statistics. Today we start chapter 5, which is probabilities, so get ready to take some notes. We're going to start off with what probability means. So first of all, what is the definition of probability and the notation we use? We use a capital P to indicate the probability of, and in parentheses it's whatever we're looking for the probability of. A capital E stands for event. It's a very generic way to write the probability of something happening. When we actually use a problem, we'll plug it in with something specific. The probability of an event occurring is equal to the number of ways to succeed divided by all possible outcomes. All possible outcomes. And again, an outcome is simply one way in which the event can end. If I roll a die, there are 6 sides in a regular die, so there are 6 possible outcomes. If I'm looking for the probability of rolling a 5, there's only one way to roll a 5 out of 6 possible outcomes. Probability of success, 1 in 6. Pretty straightforward, right? There's also a complement. Now there's 2 ways to look at the complement. There's either a little apostrophe, a prime marker, or if you're in calculus, a derivative mark. Or you can also look at a superscript of the letter C. It stands for complement. The complement of an event occurring is that the event does not occur. So what would the probability of an event not occurring equal? Well, it's 1 minus the probability of the event occurring. These are the same thing, so it's the same notation there. And there's a good reason for it. Either the event will happen or it won't. So since it'll either happen or it won't, they add up to 1 for 100%. The probability of an event occurring is a number between and including 0 and 1. It's going to be either 0, which means it's impossible, up to 1, which means it's guaranteed, or something in between. Okay? Now, the number of outcomes, it could be anything. If I flip a coin, there's only 2 outcomes. If I roll a die, there are 6 outcomes. If I'm drawing a card from a deck of cards, there could be 52 outcomes. There's obviously contingent upon the problem. However, if you add up all of the individual probabilities in the chain, what do you think it's going to add up to? I say P of X here because it's not just an event occurring. In this case, it's a particular outcome. So if I add up the probability of rolling a 1 and a 2 and a 3 and a 4 and a 5 and a 6, what's it going to equal? The number 1. The sum of all the individual probabilities within an event will add up to 1 for 100%. Okay? Write that down, pause it if you have to, make sure you have this information in your notes, and we move on. The denominator in the probability formula here, all possible outcomes, has another name also. It's called the sample space. So all the events in the sample space constitute all possible outcomes. The denominator of the problem is the sample space. The numerator is still the number of ways there are to succeed. Is there always just one way to succeed? No. If I'm rolling the die and I'm looking for, say I'm playing a game where I win if I roll a 1 or a 2. All right, well now there's 2 possible ways to succeed out of the 6 possible outcomes. So the probability of my success is 2 out of 6, or 1/3. What if the only way to fail is rolling a 5? Since there's only one way to fail, there's 5 ways to succeed. 5 and 6 is my probability of success. 5/6, roughly 83%. there's lots of different outcomes. There's lots of different ways to express the probability. Moving on from there. Let's see. Do I want to go to that? Yeah, I'll go to that. Okay. There's something called, and it's a correct label. It's just a very, I don't know, non-creative label. It's called the law of large numbers. Okay. What does that mean? Well, you know how I said the probability of rolling the number 5 is 1 in 6? Obviously, when I roll a die, it could be anything. What if I roll it 6 times? Will I get 1 in those 6 trials to be the number 5? Maybe. Maybe not. I could get no 5s. I can get 3 5s. I can get all 5 5s. I don't know, or 6 5s in this case. It is not a guarantee. Probability is never a guarantee on the short run. If I perform a trial once or twice or 3 times, there's no guarantee that I'm going to see the theoretical probability, which is what should happen in theory. There's no guarantee I'll see it manifest. But if I roll that die, let's say 60 times, and it's a fair die, then 1 in 6 should be the number 5. So if I roll it 60 times, I'm likely to see 10 5s, or close to it. It might not actually hit 10 exactly. It might be 9, or it could be 11. It could even be a little further away. But the more I perform this trial, the closer our empirical probability, which is what's happening, will come to the theoretical probability, what should happen. If I roll that die 6,000 times, again, there's no guarantee that exactly 1,000 of them will be the number 5, but it will be very close, super close. So the more you perform the trials, the larger the number of trials becomes, the closer our empirical probability will come to the theoretical, the law of large numbers. In the long run, we will see this probability emerge. And if we don't, it gives us evidence of bias. If I roll that die 6,000 times, I expect to see 1,000 5s. If I see 990, that's close. 1,015, it's close. But if I only see like 720, that's really far away from what I expect. And 6,000 trials is a large number. This is giving me concern. Then I'll look at the rest of the distribution. Well, what's coming up a lot more than it should? What we have here is an unfair die, a weighted die, something that's designed with bias. The law of large numbers helps us understand what we should see in the long run, rather than what we do see when we run the trials. Short run, you might not see what you're supposed to see. Long run, you should. Now, I want to show you how we do simulations with probability models. We're going to use the random digit table. So I've attached a little snippet of it to the Google Classroom so that you can use it. It's in your textbook. It's one of the last pages in the index. Here's what we're going to do. I am going to describe an experiment. We are going to be rolling a die. Okay. Now, let's say that my die is a standard die, 1, 2, 3, 4, 5, and 6. And I am going to find success, I win the game, if I roll the number 2. 2 times out of 5 trials. That sounds like a strange game, but that's the game we're going to play. So I want to know, how likely is it that I can actually roll the number 2 times in 5 trials? So I'm going to roll the die 5 times, and the probability of getting a 2 is going to be what I'm looking for. Now, yes, of course, it's an experiment you could run, but I'm also going to model it with a probability model. Here's the reason why. If you do something in practice, you might see a different value than you should see in theory. And it gives us reason to, let's say, suspect that there's bias. Or just, let's just say, a wrong hypothesis. Maybe it's not true anymore. Maybe it is, maybe it isn't. Sometimes, like rolling a die, it should be pretty consistent. Other things, less so. So I'm going to assign values. I'm going to use the random digit table and assign values for success and failure. Now I'm rolling a die. Let's keep it easy. The number 2, that's success, okay? So 1, 3, 4, 5, 6, that's failure. I'm going to use the random digit table, which means it has numbers 0 through 9, and I don't want to use 0, 7, 8, or 9. So those are numbers we omit. When I find them, I skip them because they're not within my range. Now, we don't throw away repeaters in a problem involving probability simulations. We're not sampling from the population. We're not going to pull person number 2 out of the audience and therefore omit any future person's number 2. That's not the way it works. The number 2 represents success this time. So if I get a success, I don't throw it away for the next time. It still counts as success. The other numbers are still rolling those numbers. I'm going to start with line 101 on the random digit table. Now I'm going to write down over here what line 101 looks like, and then we'll go through that. So it's, let's see, 19223 95034. I hope I am not writing these incorrectly. 05756 28713 96409 12531 42544 82853. Okay, now the number 2 is success. 1, 3, 4, 5, 6 is failures. 0, 7, 8, 9 is omit. Here's what we're going to do. I'm going to roll the die 5 times. And I'm going to count out of those 5 times how many times I win. How many of those 5 rolls are 2s. I'm going to start off by omitting the values that I can't count. So 9, 9, 0, 0, 7, 8, 7, 9, 0, 9. Is that an 8 or a 5? Can't read my own writing now. That was a 5. Okay, those are all good, and that's no good. So I've crossed out the numbers that shouldn't appear on my die. And if I made a mistake, I'll find it as I go. Okay, so I'm going to look in chunks of 5. Now, again, the ones I omitted don't count, so I can't count them. So I have 1, 2, 2, 3, 5. See that? This is the end of the first trial. And I did find 2 2s. Well, look at that. On my first run out the door, I got 2 in 5 to be success. I have 1 already. The next one is 3, 4, 5, 5, 6. Now, 3, 4, 5, 5, 6, there were no successes at all. So in that run of 5, I got no 2s. 2, 1, 3, 6, 4. Well, there is a 2 there, but there's just 1 of them. So I'm looking for getting 2 2s. That doesn't work. 1, 2, 5, 3, 1. Again, there's 1, 2 here, but not 2. 4, 2, 5, 4, 4. There's a 2, but not more than that. And I ran out of numbers for me to write down, so I'm just not going to worry about it. So we got 1, 2, 3. We got our 5 trials right there. I didn't need those numbers. Right? 1, 2, 3, 4, 5. Yep, we got 5 trials of rolling the die 5 times. And I'm looking for how many times it got 2 successes out of the 5 trials. It looks like I only got the 1, right? And let's just double check. 1, 2, 2, 3, 5. That worked. 3, 4, 5, 5, 6. There's nothing. 2, 1, 3, 6, 4. There's only 1. 1, 2, 5, 31. There's 1. 4, 2, 5, 44. There's only 1. Okay, great. So in one of my 5 trials, I got exactly 2 successes. So my little simulation generated a probability of 1 in 5. So the probability of getting 2 2s, as described, was 1 in 5, or about 0.2. Okay, it was just a theoretical simulation. The actual probability, and we'll get into how to figure this shortly, but the actual probability of getting 2 successes as described is approximately 16%. My simulation was actually pretty close to the actual truth of the probability model, but it didn't have to be that close. I could have found 3, I could have found 0. 5 runs isn't a lot of runs. But the more I perform that trial, the closer it will become to the theoretical, which in this case is about 16%. So if I ran 100 trials of 5-digit simulations, I should find out of 100, about 16 of them will have exactly 2 2s. Okay. That's what the law of large numbers and the random digit table simulations show us. Your job on the homework, 5.1a, the worksheet, it goes through problems like these. Give it a shot. If you have any problems or struggles with the probability models or the random digit table, of course, that's what we're here for, to work out the kinks. Log into the Google Meet if you have questions. Have a great day.